Okay, so let me ask you something. Have you ever picked up a new skill, maybe in a video game, and it just clicks? But then you try to read, I don't know, a legal document, and it feels like your brain just hits a wall? Well, it turns out that feeling of difficulty isn't just you. Today, we're going to look at a really cool scientific model that can actually measure how complex an idea is.
I mean, really think about it. You can tell a cat from a dog in a split second, right? But try explaining something like the rules of cricket or American football to someone new, you could be there for hours. So what's really going on? It's not just about us, it's actually about the hidden structure of the ideas themselves. And believe it or not, science has a way to map it.
Let's make this super simple. Look at this example. On the left, the rule is just all red objects. That's it. Easy. Your brain gets it instantly. But now look at the right. The rule is any blue square or any red triangle. Whoa. You can almost feel your brain having to fire up a few extra circuits, right? You're juggling multiple conditions at once. That little bit of mental friction. That's exactly what we're going to unpack today.
And this brings us to a really big idea. That feeling of something being hard to learn isn't just in your head. It is a real, measurable property of the concept itself. And scientists have a name for it: structural complexity.
Yep, you heard that right. We can basically put a number on how tough a concept is just by analyzing its internal logic. The more twists and turns, the more ifs and ors you have to keep track of, the higher that structural complexity score goes.
So how in the world do we actually measure this? Well, researchers have come up with this really powerful framework to do exactly that. It's called the Categorical Invariance Model. You can kind of think of it as an equation for understanding.
So the Categorical Invariance Model, or CIM for short, basically says that a concept's difficulty comes down to this constant battle, this tug of war, between two main things: how many items fit into the category, and how simple the rule is that defines that category.
So factor number one is cardinality. It's just a fancy science word for size. So think of a category like all the stars in the sky. The cardinality there is massive, right? The more things that fit into a category, the more there is to potentially learn, and that can really crank up the complexity.
And then you've got factor number two, categorical invariance. This is all about how simple and consistent the rule is. A really simple, elegant rule like, is it round, has super high invariance. But what about a rule like, is it a mammal that lays eggs? Well, that only really works for the platypus and the echidna. It's a weird, specific rule, so it has very low invariance.
And this is where it gets really, really cool. You can see how these two factors are constantly pushing and pulling against each other. As you add more items to a category, higher cardinality, the complexity wants to go up. But if the rule that defines that big category is super simple, if it has high invariance, that pushes the complexity right back down. It's this beautiful balancing act that ultimately decides how easy or hard something is for us to learn.
All right, so how does this model actually do the math? Let's take a quick look under the hood at the engine that makes this whole CIM thing work. And I promise, it's not nearly as intimidating as it sounds.
Okay, so the technical term is the boolean differential operator. I know, it sounds like something straight out of a sci-fi movie. But for our purposes, you can just think of it as a logical engine. Its whole job is to take a rule, pop the hood, and count how many moving parts are inside. And here's basically how it works, in 3 simple steps. First, you feed a concept into the model, like our blue square or red triangle rule from before. Second, the engine gets to work, analyzing the logic, breaking it all down. And third, it spits out a number, a precise simplicity score that tells you exactly how complex that rule really is.
And this whole collection of simplicity scores for a concept gets a pretty cool name, the logical manifold. The best way to think about it is like a topographical map of an idea. It shows you all the mountains of difficulty and all the nice, easy valleys of simplicity. It's like a blueprint for understanding.
So, we've got this incredible model. It can literally measure the complexity of ideas. But what's the big deal? Why does any of this matter in the real world?
This quote from the research paper really gets to the heart of it. The whole point is to create a single, unified theory that can explain and maybe even predict why we struggle with some ideas and not others. It's about taking the guesswork out of learning and maybe, just maybe, turning the art of teaching into more of a science.
And it's really important to remember that the CIM isn't the final answer. It's just one step, a really important one, on a longer scientific journey. You can see it grew out of an earlier theory,
and it's already paving the way for even more advanced models in the future. It makes you wonder, what will we be able to understand about learning 10 years from now? So if you're going to take away just one thing from all this, let it be this. That struggle you feel when learning something new, it's not random. It's predictable. It's all about that tug of war between the number of examples and the simplicity of the rule. And this model gives us the tools to actually measure that.
And this whole thing leaves us with a pretty deep question to chew on. What's the bigger deal here? Is it that we're creating a model that's getting really good at predicting how our own minds work? Or is it that this model might be showing us something fundamental about the nature of complexity itself in the entire universe? It's a thought that kind of pushes beyond just psychology and gets into some really fascinating territory.